Okay, so talking about the course, the webinar is a 5-day crash course on quantum computing. This course will provide an introduction to quantum computation starting from basic to intermediate level. Students will learn about qubits, quantum gates, entanglement, and many other topics, including some major quantum algorithms such as Grover's and source algorithms. The course will incorporate significant discussions about other interesting quantum information processing topics and various open questions in the field. Participants are welcome to ask questions and clear doubts. I wish you all a fruitful 5 learning days ahead. The mode of communication is both English and Nepali as per one's ease, and all the participants are encouraged to immerse fully into the course. Thank you.
Thank you, Shrudeep. Now it's time to start our course. I would like to request Mr. Kiran Adhikari sir to carry on with his program.
Okay, so thank you, Rosni. So am I audible? Should be right.
Yes, sir.
Yeah, okay. So first of all, thank you for inviting me here. And it's actually my honor to be here because I also did my high school in St. Xavier College, and actually it's kind of feeling like nostalgic, so and it's actually I'm really happy to contribute to the physics in St. Xavier College and also in other colleges in Nepal as well. So it's my pleasure and it to be here. And thank you for inviting me. Um, so I will try to share my screen if it's okay. So am I audible? Should be.
Yes, sir. Sir,
So,
what you have echo?
yeah. Um, okay, so I will start. Yeah, so now it's fine, right?
Yes, sir.
Okay.
It's okay.
Okay, so what I want to do is like, so there are some topics and in quantum computing, and the first of all, I need to know, like, I mean, if everyone is from bachelor or master, or like, what is it? So I guess like most of you are from bachelor, right? Right. Okay, so and I will try to present in such a way that, for example, like you don't need to know anything about quantum mechanics or, I mean, or things like that. Okay, so that's good. So, and one thing I need to clear is that if you have questions, then you can immediately ask. Okay, so you don't have to worry. I mean, then you can also put in the chat, and I will look after some time, and then I can answer it there. And it's supposed to be like a very I mean, it's not supposed to be very formal. Like it's supposed to be interactive. So please feel free to stop me like whenever you want, and it's okay. And the course will be like 2 hours each day, and there will be 15 minutes break. And the first day we will talk about we'll just talk about quantum mechanics, and we'll talk about quantum mechanics and some qubit, single qubit, and then later on, like we will start to talk about something more advanced. Okay, so then we will in the next day we will talk about some other algorithms, and in third and fourth day we will be more serious, and then we will see a concrete example, something known as source algorithm. And in fifth day, then we will finally talk about, like, I mean, in fifth day, the plan is to give you overview of what is going on in the quantum computing field and this kind of stuff. So the first day will be more about a review. I mean, usually in bachelor course, people only take like the quantum mechanics at the end of the semester, right? And at the end of the bachelor. So I will give you a very quick overview of quantum mechanics and what it is about, but I won't go into the detail because it's not possible. Okay. So the first day I will just talk about quantum mechanics, and maybe like you know a bit about quantum mechanics. Okay, so maybe you have heard a bit about quantum mechanics. So I mean, it's for us, like we really don't need to know a lot of quantum mechanics. So we just need to know about some basic features and then some basic things. And if we need it, then we will keep on top of it, right? As we will keep developing on top of it. So it's not necessary that you already know a lot about quantum mechanics. But okay, so what do we have in quantum mechanics? And usually, like in quantum mechanics, everything is described by this what is known as wave function psi. And if you don't know, so what is a wave function? So the wave function it's a probability distribution. So in quantum mechanics, like we always talk about wave function. So we are never sure about where the particle is or where it is. So we can only talk about probabilities, and everything is governed by probabilities. So, sorry, so is it audible or? Okay. Okay, so I'll continue then. So in quantum mechanics, like we have to talk about probabilities. So, and then, okay. So what do we have? Like this psi of x is some kind of a function, and then it just tells you the probability of your particle. So we just have this wave function, and for example, like it has some shape like this, right? Some shape like this. So this is a wave function, and then this is a position, and then this is some wave function psi of x, and you plot this with this function. And what does it tells you? It tells you like so. So this wave function gives you all the information that you need about your particle. I mean, if you have a quantum system, then you want to describe it, and if somebody gives you the wave function, then you know everything about the quantum system. So you don't need to know anything more. In fact, like if you even have the entire universe, and if somebody gives you wave function of the universe, then you know everything. But what does the wave function gives you? It gives you probabilities. So you never know like where the particle is. So instead of that, like for example, so this is x, right? And then here A, and this here's B. And then somebody asks me, so what is the probability of this particle to be in this position between A and B? Then what you do is you just need to compute a wave function, and then so you just need to integrate over this curve and then square it, and then when you do that, then you get the probability. So all you can say is, okay, so my particle has this much probability to be at this position, right? So for example, I mean, if you have a wave function like this, then most likely your particle will be at this position, but you don't know it. I mean, until you perform the measurement, all you know is like probability. So it can be here. I mean, it has very low probability to be in this region, but there is a probability to be there. Okay, so that's the wave function. So wave function, it gives you wave function. So that's the difference between classical and quantum mechanics. So in classical mechanics, for example, like I'm sitting on top of a mountain and I throw a ball, and then the Newtonian mechanics tells me like exactly where the ball will land. So if you provide me initial speed and position, then using using Newtonian mechanics, like classical mechanics, it will tell me like where the ball is going to land, right? I mean, that's just so classical mechanics. But in quantum mechanics, what we have is you won't know where the ball will land, but you can know probability. So you can know that, oh, there is some probability to land at this region. So that's the wave function. So and then so there are like very few rules in quantum mechanics that you need to understand. So first of all, so everything is described by this wave function psi x, right? And it also tells you the initial condition. So so just like for the ball, you need to specify like what is the position and momentum, right? The initial position, momentum. So you also need to do that in quantum mechanics. In fact, in any physical theory, you need to do that. So first of all, you need to describe your state psi of x. So that's like That's my initial wave function. And then after some time, like, I mean, I don't know what is there in the box, but maybe there is some electric field, magnetic field, whatever, right? So then it interacts with this wave function, and then it will evolve into something else, psi prime of x, right? And how does it evolve? It's given by Schrodinger equation. So Schrodinger equation will tell you, Schrodinger equation will tell you like what will be the wave function at some time. And then in the Schrodinger equation, you can include interactions and everything. So that's the second condition. And the third condition is that, I mean, it's not enough just having the wave function after some time, but you also need to know like how do you, I mean, at the end of the day, you go in the lab and you perform measurement. So you need to know like how do you, I mean, you need some kind of rule to tell you like what is the outcome, right? So then you have some probability of measuring x. It's given by. So there is 3 rules. So you have initial condition, and then you have the final state, which is given by Schrodinger equation. So, and then after that you have like this probability, which will tell you what it. So, for example, in this case, so I started with this kind of wave function, and then I don't know, after Schrodinger equation, like, I mean, my wave function evolved into something else, right? So maybe there was interaction with this ball, and then, I mean, some electric field, magnetic field, whatever, some kind of field interacted with this ball, and then after some time, this ball is at some other position, but it will be described by some other wave function, something like this, right? And this is psi of x, and this is the second state, so that you get psi prime of x. And now, like, I mean, what will be the I mean, where is the maximum probability that your ball will be? I mean, initially it was here, but now because, I mean, the maximum probability will be at this position. So you get the basic idea. So you have this wave function which will tell you probability distribution. So I mean, Schrodinger, because quantum mechanics, it's deterministic, but the outcome are probabilistic. So that's the thing. So that's everything I want to say about quantum mechanics. And now, like, I mean, we will just try to, I mean, we will make it more and more simple so that you can actually understand and appreciate what is quantum computing and these things. So if you have questions about quantum mechanics, then you can ask. But I'm not going into detail. So that's everything I want to talk about the quantum mechanics. So I mean, all you need to know is that there is wave function and it's probabilistic and it evolves with Schrodinger equation, and the equation has to be unitary and so on, right? So that your probability gets conserved, and at the end you perform measurement and it will tell you whatever probability of some particle. So that's the thing. So, and the wave function will tell you the probability. Okay. So there are like 2 simple rules. I mean, so I just mentioned before. So first of all, I mean, these 2 simple rules that I mentioned here are not just particular to quantum mechanics, but it's true for any physical theory. So now, like, I mean, what I'm trying to do is to make it more and more like abstract, and then remove the formalities and so on. So you can always think of quantum theory as just some kind of modification of classical probability theory. So I just mentioned, right? So in quantum mechanics, we talk about probability. So I mean, it is in some sense a modification of probability theory. And what we do here is we replace these positive real numbers by complex number. So you replace this positive real number by complex number. I mean, so in classical probability theory, I mean, in probability theory, maybe that what you learned in mathematics and so on. So the probabilities are always a real number, right? So, and then they have to sum up to 1 and so on. But here, what we do is we will twist it a bit because this classical probability theory cannot explain what we observe in quantum mechanics. So we need to modify it a bit. And the way we are going to do is, I mean, it's not the way we are going to do it. It's in fact what the experiment suggests us to do. So you have to replace these positive real numbers by some complex number. And then we won't call it probability right now, but instead what we call it amplitude. Right? So you have amplitudes, and then the way to convert amplitudes into probability is just take the absolute value and then square. So they can be complex number.
So now, like here, I mean, so for example, your probability in some sense can be negative, and they can even be complex number. And I mean, so this is first thing that you have to understand. So it's in some way like we're trying to modify the probability theory in quantum theory. Right, so by replacing this positive real number with complex number, and this has some effect, and we will see that this is what makes quantum computing interesting, because if you can change the law of probability, then you can expect something interesting to happen. Right, so these are two rules, and these are rules not just specific for quantum theory, but like I said, it's true for anything, any physical theory. So what I mean, if you want to describe by probability, then it's true for anything. So let's say like you have some events happening. So you have some it's like this. So you have a sequence of independent steps, and then so you have sequence of independent steps. So for example, you have some particle which has a probability to go to this position with some Z1 amplitudes, and from here it has some amplitude to go to this position, and that's with Z2. Then the total amplitude will be just multiply the amplitude Z1 times Z2. So this means that if you have independent steps from here to here, then you can just multiply the amplitude for each step. So that's one rule. And the second rule that you need to do is, and let's see like what happens if you have two different, sorry. And if you have like two different ways to reach to a same point, then how do you do it? So let's say these are Z1 and Z2. And then in this case, what you need to do is simply add up the amplitude, right? So here, I mean, if you have independent steps, then you are going from here and to this position, then you have some amplitude to go there. Amplitude in some sense is like a probability. So you have some probability to go from point A to B and B to C. Then if they are going in independent way, like for example, it doesn't, the probability from B to C is not dependent on A to B. So that's what I mean. So if you are, then the total amplitude, you just need to multiply Z1 times Z2. But if you have like several alternative ways to go to the one path, then you need to add up. Now you can think of like any kind of physical process, and with these two simple rules, you can pretty much explain like everything that happens in atom, to molecules, to even in the gas, even in the like stars or whatever. So because I mean, let's just think about something more complicated. Right, like if you think of something, I mean, some kind of event happening like this, and then each path, for example, here. So here you have two options to go from here to here. Then what you need to do is add up the amplitude for this one, right, and add up the amplitude for this one, and then so for example, this is then Z1, Z2, Z3, and then the amplitude to go from here to here is what, Z1 times Z2, Z3, right, and then from here, let's suppose Z4, then they are happening at independent ways, so you need to add up. So this way, like you can describe what is the probability to go from A to B. So in fact, like any kind of physical system, you can describe with these two simple rules. But what you need to understand is like you are not multiplying the probabilities, but instead you're multiplying the amplitudes, and this changes everything. Okay, so yeah, so I just wrote here like these are very simple rules, but these are just two rules, right? I mean, then with these two rules, you can pretty much explain any kind of physical system. Because what can happen in a physical system? So it just processes of independent or I mean, you can like any kind of system, you can always divide into such small steps. So that's what I'm trying to say. Yeah. Okay, so now like let's see. So let's try to see like what we just said. I mean, so classically you have some probability and it's a number between 0 and 1. I mean, it's okay, right? I mean, that's what we studied. It's fine. And in quantum, like the difference is that they can be negative and they can even be complex number. And the quantum computing, it's all about we are trying to exploit this phenomenon. Okay, so in classical computing, I mean, it's just some theory, but let me just explain you. Like in classical computing, there's a thesis called extended Charles Turing thesis, and it says that a probabilistic Turing machine can simulate any realistic model of computation. So what it means is that if you have some kind of a physical system happening, then if you have a computer, then the computer should be able. I mean, computer. By that I mean like a Turing machine. So a computer or whatever, it can, it should be able to simulate any kind of a physical phenomenon in a polynomial time. So polynomial time means that, okay, so it should not take a very long time to simulate any kind of physical system. And that's the extended Church-Turing thesis, and it's very, very fundamental to classical computation theory. So, and then quantum computing is about proving this wrong, because if you have any kind of a physical system, for example, if you have some kind of a gas molecules or whatever, right? So if you can simulate it in a computer, then there is no need for quantum computing. Right? So because if you have a quantum machine and then if you have some quantum phenomenon happening, and then if you can actually simulate it using classical machine, then you don't need a quantum computing to do that, because you can just simulate it. But instead, like if you have, so quantum computing is about proving this thesis wrong. So instead of having extended Church-Turing thesis, what we need is like a quantum extended Church-Turing thesis, and which says that if you have like any kind of a, and which says that a quantum Turing machine can simulate a quantum computer. So in that direction. So this is important. So now, like, so if you have questions up until now, like, you can just ask in the chat, or you can just unmute as well.
So can you explain that Turing machine part once again?
Yeah. So okay. So maybe like, okay. So this thesis says that, okay. So you have some Turing machine, which means, okay, for now, let's just assume that it's some kind of a computer, right? Turing machine is some kind of a computer. And then you have some physical system phenomenon that's happening in the reality, physical phenomenon. It can be, for example, like, I mean, whatever, so there is some gas molecules inside the chamber or what, so this thing, right? So, and then you have some kind of physical phenomenon happening in a real thing. And the extended Church-Turing thesis says that if there exists something which is happening in a physical phenomenon, then a Turing machine should be able to simulate it in a polynomial time. Polynomial time means that so it should not take a really long time to simulate that kind of phenomenon. So this is extended Church-Turing thesis, and our like current model of computation is all dependent on this, because if you have one machine which is based on one kind of hardware, and you have some other computing machine which is based on some other kind of hardware, or uses some other kind of language, right? So then this thesis says that they are all equivalent. So it doesn't matter, like, I mean, so it doesn't matter like how you try to implement your physical computers, but I mean, these are all like polynomially equivalent to each other. So that's why like it's quite important in classical computer science. And then this thesis said that if you have some kind of physical system, that's a physical phenomenon that's happening in reality, then a computer should be able to simulate it efficiently. But now, like, so instead of, so this is okay. So this is true for classical physical phenomenon, but instead, like, let's say what happens if we have a quantum physical phenomenon? Then the question is like, can Turing machine, which is like classical computer, simulate this quantum phenomenon or not? Right? Because that's the question. So the reason is I mean, the reason it doesn't seem that it's possible, I mean, it goes all the way to Feynman. And he was studying, for example, like how to simulate molecules and so on. So he was interested in that. I mean, and in molecules or in chemistry, for example, so there are so these are like all the atoms or electrons, right? So and then to describe this electron or atom, I mean, if you have, let's say, 20 or 200 atoms here, and then you need to know the wave function for 200 atoms, and then they interact in a very crazy way. So now the question is like, can a computer simulate this or not? And as far as we know, like it's very hard for a classical machine to simulate this. I mean, there are no good algorithms to simulate this many body system efficiently. And therefore, the question is like, if there is a quantum phenomenon, can a classical machine simulate it or not? And if they cannot simulate, then this means that you have some other kind of Turing machine which you can build, and the other kind of Turing machine can be like quantum Turing machine. So, and this gives the way to quantum computing. I mean, it basically says that if you have a quantum computer, then it will perform better than classical computer, because classical computer cannot simulate a quantum system, but quantum computer can simulate it. So is it clear? I mean, it's in that direction. So is it clear?
Yes, sir.
Okay. So today, like I will not talk about. I will just go through like, up to qubit, right? And then after some time, like after I think a half an hour, we'll take a break for 15 minutes. And then tomorrow, like I will start talking about multiple qubits, entanglement, and so on. But today, like we'll try to maintain the base. Yes. So that's why, like I'll also go through double slit experiment, and then I mean maybe you already know it or not, but it's quite fundamental. And it's also like just using those rules that we discussed before. I mean, you should be able to understand it. Okay, so in a double slit experiment, what do you have? So you have okay. You have source, and then you have a detector, right? So and then from source you emit lots of particles to the detector, and then you observe at the detector. So there's a detector. For example, you can send photons through it, and then so detector, it can be a wall or what, so something like this. But for now, like let's just assume here's a point, detector D, and then it can take two paths, right? So it can go from here or here. And then we discussed before that how do you make, so it can, from source to detector, it can take two paths. So it can go from Z1 or Z2. So you have source, you have detector, and then you emit lots of particles from source. And right now we just have double slit, so it can only go from two paths, and we assign some probability to each path. And it's not probability, it's amplitudes, but we will see. So and then so let's look classically what happens. Classically, we know from Bond's rule. So, and the probability to go from source to detector from this first slit A, and I will call it B. And the first slit is P1, right? And that's, we just need to take absolute value of Z1, and that's the probability to go from source to detector from path A. So this is path A, and this is path B. Okay. And then what is the probability to go from source to detector from path B? Then it's also P2. So Z2 is correct. And in classical probability theory, so what happens? So these are from so you are taking like alternative paths. So in that case, what you need to do is you just need to add up the path, add up the probability. Right? So remember, where was it? So you have two rules. So if you have several alternative ways to go from source to detector, then you just need to add up. And if you have like several independent steps, then you need to multiply. So we just follow this rule. And for now, like we just need this rule, right? We don't need this one because we just have two ways to go from source to detector, and we just add up. So that's what I'm doing. So now, like if I have something like this, probability from go to source to detector P1 and then from here P2, then I just need to add up, right? So classically, what happens? So total probability to reach from source to detector, I mean, this point is P1 plus P2, and which is just this term. Right? So now, like now you can immediately see the problem here, because you I mean you might have already know from experiments or from somewhere else that from if you have source and if you have a detector, what you see is some kind of interference pattern at the detector, right? So you need to see some interference pattern. But now, like your probabilities are always positive, because this is positive number and this is positive number. So at any point in this detector, in this for example, if you consider here or here or here, and the total probability is always going to be positive. So this means that there is always some probability to land at any position over here. And this means that you will never get the destructive interference. So you will always have like, you will always have some signal at the detector, right? But that's not what you observe in the lab. Like you observe some kind of a interference pattern. So you have a constructive interference at the center, and then you have some kind of I mean, you have like a constructive and then destructive. So you have some signal in some point, and in some other point you don't have signal. So that's what you observe. But classical theory is just telling us that you just need to add up the probabilities. But then if you do that, then you won't get interference pattern. So that's the problem. But now, like I mean, but we discussed before that it's not the probability that you need to add, but you need to add the amplitudes, right? So what you need to do is actually, I mean, the true way like to do this calculation is consider this quantum probability. So P equals to Z square, and Z is actually Z1 plus Z2 square. So this is the difference. So here we had this condition, but now like we need to sum up Z1 plus Z2 and then only take the square. This is so total amplitudes to go from S to source to detector is Z1 plus Z2. And the probability is you need to take this. So you don't do this way, like you already take the probability and then sum up, but rather what you do is you Z1 plus Z2 and then only you square it, and then what you see. So for example, like this, you can write this Z1 and Z2 in this polar form. So I'm just writing, these are complex numbers, so I can write this in polar form, right? This is Z2. And now like I will expand this term. So what happens? So right now, like I'm just expanding this, and then this is just a usual complex number. It's that's how you take the amplitude. That's how you square it. And then this term, it's this one. So P1 plus P2 is this one, right? So this is just P1 plus P2. So this term, and this is classical term. And then if you do it and then include this polar term, then what you get at the end, it's at the end of the day, it's something like. And then you have like in addition to this classical term, you also get, I mean, it's quite easy to do. Okay, so all you have to do is insert this over here, and then I mean, I think you know how to do it. So I won't go through it. But if you do this algebra, a little bit of algebra, then what you will get is you have this classical term, and then in addition you get this extra term. So classically you just had Z1 square plus this term, right? So here you get this term plus something else, and then this term, what we will call its interference term. And now, like, you can already see the difference from because this one, this term can be positive or negative because this is a cosine of some angle, right? So this term can be negative as well. And then if it's negative, then you can, for example, then the total probability can be 0 as well. But in this classical case, you always had the positive. But here you can have a probability to be 0, but it depends on this phase angle. So this just means that at some point there will be, I mean, maybe like here it will be a constructive interference, but at some other location there will be destructive interference. So by just these two simple rules, you can already see that you have this extra interference term, which can make your total probability at the end to be even 0 at some position. And and that's the difference between classical and the quantum probability theory. And if you are really changing the probabilities, then maybe like if you use this for quantum computing, then you will get different answers. And this means that, for example, so and then the whole trick or whole idea in quantum computing is this interference. So what you want is that you want to amplify the answer, right? The correct answer. Then that basically means that you are trying to so you want a lot of probabilities at your correct answer, and then you want very little probability to be at the wrong answer. And when at the end, when you perform the measurement, then when you go and look at the measurement, and that means that when you take at the detector, then it should be such that the probability to get correct answer will be huge. And how do you do that? By changing this interference pattern. So basically so the whole trick is just changing this interference and then getting the correct answer. I mean, almost every quantum algorithm uses this trick. So that's why it's quite fundamental, and it's really simple because it's just interference. Yeah. So if you have question about this, then okay. So it's just what I wrote before. I mean, so the interference is really important. So I mean, there are like lots of confusions about quantum computing. I mean, some people think that, oh, so maybe like usually people say that, oh, in quantum computing, what you do is you are performing answers, like you have some 0 and 1, and you also have superposition, and then you're trying to do like computation in all possible alternative way, right? Like something like that, in some direction like that. But that's actually not true, because this you can already do that in classical computing. So you can do 2 computation at once, even in classical. I mean, that's what they do in this something known as probabilistic Turing machine. So in probabilistic Turing machine, they already do that. So in probabilistic Turing machine, you are also trying to do like 2 answers at the same time. So this means that, for example, you have some position A here, and then you have 2 options to go here. And then there's some probability. So with some probability P1, you would try to go through this path, and then with some probability P2, and then you take the second path, and then you look for the answers in both paths, right? So I'm just saying that, so this idea that you are performing 2 computations at the same time also exists in a classical machine, but it's just that in quantum you have these probabilities which can I mean, there are like, in addition to these classical rules, you can also have other ways that probabilities can add up. And then in classical, like what you try to do is at the end, maybe the answer is at this location, and then you try to pass through all this all this path, and then you try to do so that your answers get the maximum at this, right? So with high probability, you get this answer, and in quantum also we do the same thing, but the only difference is that these probabilities they can also behave differently than the classical one. And so that's everything about quantum machine. So it's not that you are doing 2 computations at the same time or 100 computations, because classical already does that. So this is it. So and also, I mean, this is a bit of so you have this in classical computer science. I mean, the most powerful machines that we have right now are probabilistic machines, and then in addition, we now like with quantum, then you have like a quantum probabilistic Turing machine, and then what you try to do is like and then you want to find some interesting applications of a quantum machine, right? So maybe like there are some applications that you can do which you cannot do with classical machine, and if you get that, then it's a really interesting, and the whole research field right now is trying to find such algorithms, and it's really important then to find such algorithms. Okay, so if you have questions about this, then you can ask. Okay, so here, so I already said it. So interference is key. So the whole game is to massage your interference pattern so that probability to get correct answer is amplified. And then also the other point is that you should not measure your state immediately, because if you do that, then you know that in quantum mechanics, your wave function, it will collapse. So you should not perform measurement at the intermediate steps. So for example, like here, I mean, you already know that. So if you perform measurement at this location, then you will lose the interference pattern here. Right? So I mean, if you perform if in the double slit experiment, like if somebody is observing at the slit, then you don't get the interference pattern, because you will destroy the wave function, and then I mean, and you will not see the interference pattern. So what you used to do is like you have some source and detector, and then you perform this computation, right? So and then at the end of the computation, then you can look at the answer. So you should not look at the answer at the intermediate steps, because then you will lose the interference pattern and everything becomes classical. So if you look at the intermediate steps, then you will get the classical probability theory. So that's the thing. So now, like I will talk a bit about the notation, and this is called Dirac notation. So in Dirac notation, you always write your state like this, and then here, so here you have some Dirac, and then inside, like you can write like whatever you want. I mean, basically the idea is like, I mean, so it's very complicated to always talk about wave function, right? So because wave function is a very complicated thing. I mean, it's a very difficult to visualize it, and it's also very difficult to plot it and so on. But so what Dirac notation does is that you simplify it a lot. I mean, you remove away all those difficult things, and just say that, oh, so my wave function, like my particle, it's in upper slit, so it's going through upper slit. Then I'll just write something like here. I'll just write upper slit, right? Or if it's going from the lower slit, then I'll just write it's going from the lower slit. So anything, like if I want, so something like, and the spin of the electron, it's up, then I'll just write here up, and then it's down and down. But the idea is like, I mean, so this will correspond to actual wave function, but the wave function is very complicated. So we don't want to deal with actual wave function. We just want to simplify a lot, and then a Dirac notation does it for us. So it will take care of everything, and then we just have to follow the rules. And you have spin up, you can write like this, or spin down. I mean, also your so 0, right? So and then here like 0 means that so my electron is at state 0. I mean state 0 means could mean anything. It could mean that the electron is at the my atom is at the ground state or excited state. It could mean anything, but I just write it as a 0. It just means that it's one possible state, and then it's one could mean other possible state. Right? So for spin up, it could be up, or it could mean down. So that's the thing. So that's the notation. And okay, so and then we discussed before, like it's also possible to have a superposition of up and down, right? Up, spin up or down, or I mean so here like in this double slit, in order to explain this interference pattern, we really have to say that, I mean, it's one possible, one possible way to explain this quantum phenomenon is by saying that this electron from here went through both paths at the same time, right? So it means that it was at the superposition of upper slit and lower slit, and then only we can explain this interference pattern. Otherwise, we cannot. And so that's why, like maybe, like I mean, so you have like upper slit, and then you have a lower slit, and then I can write with Dirac notation like this, and then you can have some superposition of upper and lower, right? Alpha and beta, and this alpha and beta, it will tell you like what is the probability to be in upper slit, and then alpha, and then if you just have to take the square of alpha square, then this alpha square is the probability to be in upper slit, and the beta square is the probability to be in lower slit. And this will tell me everything about this wave function from source detector, because it will tell me like with what probability this particle is going from upper slit, and with what probability it's going from down slit, and that's all I need to know to explain the interference pattern. And I will talk more about it later on. So right now it's just a notation. Okay, so the question is, recently physicists have shown that same interference occurs with two slits in time. Yeah, I mean, I checked at it, but I don't know much about it. I mean, I need to look at it more. So I cannot tell you much about it. How does the double slit explain wave particle duality? So in double slit, I mean, in double slit, this source can emit not just photon, but you can also emit something like electron or even molecules, right? And still you get this interference pattern. So really, like the weight, I mean, the notion that wave particle, I mean, it's a bit old. So what you have to say is that wave function. So it's not the wave particle, but rather you have to talk about wave function and wave function of an electron. Or I mean, everything is like I said before, everything is described by wave function. So this wave particle duality, it's a bit old notion. I mean, and then we have to update it with wave function. Then you have to say that the wave. So initially, like you have some wave function of a electron or atom. So that this wave function is not just the wave of so you should not confuse it with something like wave of like water waves or gas waves, right? So it's a probability wave. So it's a wave that will tell you like a probability wave function. So wave function tells you probability. So it's not so it's not like something like water waves. So here, I mean, I have some electron here, and then I emit it over here, and then then I get the interference pattern at the end, and this interference pattern I get this interference pattern because of this wave function of electron. So that's how I get it. Because this wave function, they can interfere with each other, and they can even be negative at some place, and it can be positive at some place, and then when it's negative, then it's destructive, and when it's positive, it's constructive. So you have to update this wave particle duality with wave function, and then once you say that it's a wave function that really exists, then this wave function can interfere with each other, and then you get the interference pattern. But also, like, I mean, the old argument is like, I mean, these electrons, so in double slit experiment, you even get this interference pattern by sending electrons. That's so, and then electrons usually we think of it as a particle, not as a wave. But if you just use particle notion, then you don't get this interference pattern. So then, is it wave or is it particle? But the correct answer is like it's a wave function. So you have to describe the back wave function, then it makes sense. It's not a wave, it's not a particle, it's a wave function, right? So what's the light interact with so light interact with its past self on double slit. I think it's the question is about this new news, right? So they were saying that something like it interact with past self, something like that. But I don't know about that. Yeah, I mean, I have not checked that it in detail. So, and this is just so what I'm talking about. It's a double slit experiment that we observe in lab right now. I mean, so- okay, then we will take some break. Like, so if you have questions, then you can ask, and then in 3 minutes, we'll in 10. Okay, so in 5 minutes we'll take a break for 15 minutes. So. Yeah, so let's meet at 6:13 p.m. Okay, then I will start again. So welcome back. So there are some questions, and let me just clear it up. So the question is, what does probability being imaginary signify in quantum computing? So the thing is that it's not the probability, it's amplitudes that can be negative, but then you have to take the square, right? I mean, you have to take the absolute square, then that's positive. So let me say, so you have some point A to B, and then so it has some amplitude Z1, right? And then this Z1 can be this amplitude can be negative as well, or it can, I mean, it's in general complex number, so it has a structure something like A plus I B. And then what you do is you always have to take the absolute value, and then when you take the absolute value, you get the answer which is in real number. I mean, which is like between 0 and 1, and it's described by Bond's rule, right? So it's not the probability that's negative, but it's amplitude and probability amplitude that it's negative. But then the thing is that this probability amplitude, they can behave differently than if you just consider them to be, and then, I mean, if you just compare it to a classical case. You see, so for example, like this, I have some amplitude to go from Z1 to here. I mean, it can be negative as well. I mean, also there is some amplitude to go from Z1 to Z2, let's say, something like this. Okay, so let's consider a very simple example. So you have you are in point A, and then there's some point B. Then if you take this path, then your amplitude will be, for example, Z1. And if you take second path, then the amplitude to go from A to B is Z2. Now, like so if I have something like this, and then let's just assume that it's always positive. I mean, in classical case. So what do you have? So now, like the classically, what you do is, let's suppose that this is Z1 and Z2, they are probabilities, and then you need to add up the probabilities, right? So because they are from different steps, so they are going through alternative way. Then the total probability to go from A to B, it's a Z1 plus Z2, right? And then, but in quantum case, like we discussed that this Z2 can be, I mean, then you have to take the square and so on. But okay, so at least, and in the quantum case, what we have is probability it's Z1 plus Z2, and then you have to take the square, right? But let's suppose this Z2, they can be, this amplitude can be negative as well. So somehow like the Z2 is equal to minus Z1. Then in this case, there's a zero probability to go from point A to B. Even though individually from each path there is some probability to go, but if you add up the probabilities, then the to go from A to B, it's a zero. So you see, so it's really different. This, and then when you consider this amplitude, they can be negative as well, and then it really has consequences, right? So because classically, if you have some probability to go from point A to B from this path, and you have some probability to go from A to B with this path, then you will always have some positive probability to go from point A to B, right? But in quantum case, what can happen is that Z1 and Z2, they can be negative as well. And if Z2 is equal to minus Z1, then your probability to go from A to B is 0. You see, so because they cancel each other. I mean, and that's why like these amplitudes, they can be so this amplitude, they can be complex number, and in fact they can be negative. I mean, if they can be complex number, they can be negative as well, right? So, and then this has consequences, and this is what we try to use in quantum computing. Because, for example, somehow you don't want to go from point A to B. I mean, you just want to stay in path point A. Then, by doing this, you will never lose. I mean, because classically, you will always have some probability to go from A to B. If there is some probability to go from A to B, then there is always some probability. It's a Z1 conjugate of Z2. I mean, it's not necessary. So Z1 and Z2, they are independent to each other. Now, so this Z1 and Z2, they are like independent paths. but there are alternative paths. I mean, so and then it doesn't have to be Z1 and Z2 a priori. They don't need to have any relation, but I mean, what you do is like the Z1, and then you add up Z1 plus Z, and then take the square. So if Z2 happens to be some number which is, I mean, if Z2 happens to be minus Z1, then your probability is 0. So that's the thing. Okay, and there was some other questions about Dirac notation. So hopefully this point is clear, right? So can Ritika comment? So if you still have doubt, then you can ask. So it's not the probability that's negative or imaginary. It's the, I mean, it cannot be, probability itself cannot be negative, imaginary, but amplitudes, they can be negative or imaginary, and it has some consequences that we expect. Okay. So the other question was about Dirac notation. So it's in Dirac notation, upper slit written inside Kate notation. It's just for notation or used for calculation. So in Dirac notation, you can also, I mean, so I mean the idea is like it's just for notation, right? It's just a Dirac notation. The name itself is just a notation, but it's a really powerful tool. So that's why we use it a lot. I mean, so first of all, you think about wave function like describing psi x. I mean, it can be some complicated function, something like this, right? Some very horrible looking wave function. But then in Dirac notation, we just replace it with psi. Then you don't have to worry about all this extra details. And especially in quantum computing, we never have to worry about like exact wave function, because that's the job of somebody else, right? Some experimentalist to do it. I mean, because it depends on the platform. Like, for example, like if I say that 0 state, right? So something like this, and then for superconducting people, I mean, it can mean something else. I mean, because this will describe the behavior of superconductor, and for ion trap people, it might mean something else, right? So for photonic people, it might mean some polarization. Then for so we don't have to worry about that. I mean, so it depends. So right now, like we just said that if you write some state like at 0, then it just means that it's in some state 0, and it depends on the platform, right? So superconductor, and they will tell you like what 0 mean for their platform. So because we cannot say beforehand. So and then this Dirac notation provides us a tool which is really powerful, and we don't have to deal with this external stuff like hardware stuff, and we just can worry about linear algebra, basically some simple math. And this Dirac notation is like quite powerful. I mean you can formulate all of the quantum mechanics in Dirac notation and you still get the correct answer. And then I mean at the end of the day you have to use it, but I will give you some example on how to use it. So that's the thing. I mean, so if you have something like 0 plus 1, I mean, this 0 could mean like spin up or down, right? I mean, it could mean spin up, and 1 could mean spin down, or it could also mean ground state or excited state of atom, or it could even mean like horizontal or vertical polarization of light. I mean, we don't know what it could mean, and they will tell the people from optics. They will tell us, oh, this 0 state this means something for us, and then we can, and it's their job. But for quantum computing, in the beginning, like we don't need to worry about that. Okay, so now like I will give a bit more involved example of interference, and then this one will already give you a lot of ideas about like quantum computing. So now like we already have some Dirac notation. So what is happening here? So this, you can think of some kind of some atom, and then it has a two state, ground or excited state. And then you have some resonant device. I mean, so you don't have to worry about the physics right now, right? So I'm just trying to give you the example, but you don't have to worry about what's happening physics wise. So you just have to worry about like what it means for in terms of quantum computing, in terms of quantum mechanics, in terms of Dirac notation, what could it mean, or in terms of matrix or something. So the formalism like isn't it? So in any way, like you always start, as I mentioned before, in quantum mechanics or in any physical theory, you start with some initial state, and then you evolve your state, right? You have some football, and then it has some position and the velocity. That's initial state, and then you kick the ball, right? And then it moves in the air, it interacts with something else. So that's evolution, and then you observe it, and here you observe it. So you start with something, and it's a true for any physical theory. So and then you start it, you evolve it, and you perform measurement. So here. So what happens? I mean, I'll just quickly go through it. So you have an atom, and it can be in ground or excited state. It can be in ground. I mean, so this or right now here maybe like it means excited state, and then if the atom is here, then it would mean it's in ground state. And then if it's excited state, we denote it by 0, and then if it's ground, we denote it by 1. I mean, you could also do the opposite. If it's if it's ground, then I could mean by 0. I mean, it doesn't really matter. So you have an atom, and then what you have, you evolve it, and then this resonant, what it does is that it will create a superposition between the ground and excited, this part, and then it will close this dispersive. It will create some phase difference between ground and excited state, and then you have some, and then this next part, resonant device, it will close the interference. So it doesn't matter. So. And then at the end you will observe, and then the question is like, after passing through this device, what is the probability to get ground state or excited state? I mean, here it means like, what is the probability to be excited or ground state? So that's the question that we are asking here. So you have, that's a question. Okay, so you have initial state, and so you have the initial state, and then you evolve it, and then the question is, I started with the excited state. What is the probability to be in ground state after my atom passes through this device? So that's the usual question we ask in physics. I kick the football. What is the probability to land on that ground, something on top of that hill, something like that. So it's a similar kind of framework. So you have ground state, excited state, and then I pass through a device, and then what is the probability to be excited or ground, and then I denote this excited by this gate 0, and then this ground by gate 1. So we call, okay, so in Dirac notation you have this one. If you have something here, then we call it gate, and then you have something over here, then you call it bra. But yeah, so I won't go into this today. Maybe tomorrow I will go through it. So I mean, so this is also called the bracket notation, because, and then what it does is that you can take the inner product, between two vectors, and quite easily we're using Dirac notation. Otherwise, you would have to do this. I mean, if you have like 5, I mean, if you have, like, otherwise you would have to do horrible calculations, and the Dirac notation will simplify this inner product stuffs very easily. So you don't have to worry. So, okay. And now, like, and then this thing you can also write in this kind of diagram, right? So in this kind of circuit diagram. So you have 0 and 1 state. So get 0 and get 1 state. And then here, okay, so let's just look at this blue part at first, and then what is it happening? So if you look at the 0 state, and then let's suppose it start with 0, then it has 1 over root 2. Like, I mean, you have to square it, right? So 1/2 probability to be 0, right? And then 1/2 probability to be 1. So that's what's happening. That's what it's saying in this diagram. So you start with the 0 state, and then at the second step, like, you have 1/2 probability. I mean, you have to square it because this is amplitude. So I said before that you have to square it, the amplitude. So then when you square it, then 1/2 probability to be 0, and then 1/2 probability to be 1. So that's what this means. And then if you start from ground state, then it's also the similar thing. Like then it will have like 1/2 probability to be excited, and then 1/2 probability to be ground state, because then you have to square this 1/√2. So that gives the probability, right? So these are all amplitudes, and that's why this can be negative as well. So this amplitude, they can be negative, because, and then the real probability is like you have to take the absolute square, because they can be complex. So you also have to take absolute value, because I mean this means that when you observe in nature, then you won't get complex number, right? You will always get some real number. I mean, if I look at the detector, then if it's complex number, I mean, if the answer is complex number, I don't know how to interpret it, right? So it's not possible. So the final answer, like the probability, they are always in positive. I mean, they are always a real number, and they are always positive real number, but probabilities, but these amplitudes, they can be negative. So, but still here you can see that this, if you start with the ground state, then it has 1/2 probability to be excited, and then 1/2 to be ground. So then this is the first part, and the second part is so if you are in a ground state, if you are in excited state, then you will get some phase of phi0, and if you are in the ground state, then you will get some phase phi1, and it's the same thing like here. This device, it's the same thing. Yes.
Does this figure represents the same thing as figure above it?
This one and this one?
This one and
These
above
two?
one, the main one. First one.
Yeah, in this one and this one, you mean?
Yes.
Yeah. These two are like the same. So you.
And so in the first figure, does state 0 represents both state 0 and 1, or what?
No. I mean, I see what you mean. So it's not the exactly similar figure, because here I just have 0 state, right? But it could have been like 1 state. I mean, instead. So for example, then I would have to draw like 1. Then here, then the question is like, what is the probability to be 0 or 1? That.
So when we represent this single state, we just change the 0 and 1, or what in second figure?
Yes. I mean, this one is not the like correct picture in a sense. I mean, this one is just for understanding. So it just says that you have some initial state and then you pass through it. But here you are trying to represent both possible state. So in this diagram, like you can see like in this diagram you can see what happens for if you start with 0 or if you start with 1, right? And then you have like multiple paths that you need to take into account. And I will go through one example.
So then that blue one represents resonant, and red one is
Yes. So this blue one, this blue part represents resonant, and what resonant does is, if you start with so this resonant device, like if you start with ground state, then it will create a superposition of a ground and excited state. That's the job of resonant. And then this dispersive, it will create a phase difference between the ground and excited, and then this resonant will close the superposition. So then at the end you will only get 0 or 1. But there you have this phase difference, which will create. I mean, and depending on the phase difference, you will get the different probabilities to get 0 or 1. So everything that's really happening is using this dispersive. So this is creating this some kind of phase difference between 0 and 1, and then then it will create some different, like then depending on what is the phase difference that you can tune from externally, you will get a different probability for 0 or 1. So that's the idea. Okay, so here the question is like, so you started, what is the probability? I mean, everything is a probability, so it might already get boring, right? So, but I mean, quantum mechanics is probabilistic theory, right? So You have to deal with it, because you are never certain where your particle is. I mean, everything like uncertainty principle or all the things. And if you were talking about classical mechanics, then you would not have to talk a lot about probabilities. But even then, I mean, if you go into statistical mechanics or so on, then you have to talk about probabilities. So it might already get boring, but I mean, we will have to deal with it. So the question is like, what is the probability that atom, which initially in state 0, will be in state 1? I mean, this is one question. So what is the probability that you start with 0 and then you end with 1? Right. So for example, here, like if you start with excited state and then you pass your atom through this device, then what is the probability that your atom will be in ground state? Or you can also ask, what is the probability that your atom will be in what? Like if you start excited, then what is that it's excited? It doesn't matter. So yeah, that's the question. So now, like, so now, like, I'll just write here. So let uij, it denotes the probability amplitude that generates the output I with input j. So uij means I start with what is it? I start with j and then the end with I. So for example, like here, I mean u10. So you start from state 0 and then end in state 1. So that's the question. Okay, so now, like, you have to remember from before. So you start with state at 0, right? So now, like, I mean, so it's a bit of algebra. So very small algebra. So let's go through it. I mean, we just have 2 rules and how to deal with probability amplitudes, and we just have to follow it. Okay, so you start with state 0 and then end with state 1. So how many paths are there from starting with 0 and 1? So I mean, one path is you start from here, right? And so this is one possible path. And then the other possible path is this one. Okay. So I mean, if you start with a 0, then there are like 2 possible paths to reach state 1. So now, like, we have to just, so now, like, u10. So let's suppose this is the amplitude. So how do you do? So let's first do with the first path, then so then it will be like you have to multiply this with this number, right? So then u10 will be 1 over square root of 2, and then times this number ei50, and then you have to multiply with this number 1. So this is 1 over root 2, and then plus. So let's see, like and then you do the same thing for second part. So you have to multiply this with this and then this one. So what you get? So 1 over root 2 ei51, and then minus 1 over root 2. So that's what you get. I mean, hopefully it's clear, right? So if you start from state 0, and then what is the probability amplitude to start to end in state 1, then you just have to multiply the I mean, these are just from the previous 2 rules. Then what is the probability? Then probability is the square of this probability amplitude. So the probability to if you start from state 0 to be 1 is u10 square. And so now, like, you have this is absolute value, right? So because you have this complex number as well. And then this is 1 over 2. And I mean, I won't go through detail, but how to deal with this kind of case. I mean, if you know from Euler's identity, then you just need to use it. If you have something like this, then you can use this Euler identity. And then if you do that, then this will give you something sine square pi 1 by 2. So this term. So you will get something like this. So the probability is actually something like this. And then let's suppose that let phi is phi 1 minus phi 0 is the phase difference between two paths. Then the probability is just sine square pi over 2. What? So now, like, I mean, okay, so this is the probability that if you start from state 0 to reach 1, and you can see that it's a function of phase difference phi. So now, like, if you I mean, just put, let us try, like, so if phi is pi, then what is it? The probability to 1 0 is 1, right? And then if it's 0, then you have just 0. So sine 0. So if the phase difference between these two are 0, then the probability that you start from 0 to 1 is 0. And then if your phase difference is pi, then you will get I mean, the probability to go from 0 to 1 is like 1. So with the 100% certainty, if you start from excited state and the phase difference is pi, then your atom after this evolution will be in state 1. So if you start with state 0, then yeah. And then in the intermediate case, like if you have something else, then you can also have I mean, like, you can have other kind of phase difference as well. Then the probability will be different, right? So it will be some kind of a function, something like this. So I mean, and it depends on the phase difference. So that's what I want to say. Like, it depending on the phase difference, I mean, you can have like if you change your phase difference so that if I mean, depending on your phase difference, then you can have like 100% certainty of particle reaching at the state 1. Otherwise, I mean, you can also, it's also possible that there will be 0 probability to reach here. And at the intermediate case, you can have like in between. But if you consider classically, then if one path has some probability to reach state 1, and if the second path also has some probability to reach state 1, then you will always have like you will always have some positive probability. But here, because of this interference, what's happening is that I mean, it changes depending on the phase difference. So that's the whole idea. So now, like, what I will do is now finally we are going to talk about qubits. So now, like, we can also write the whole thing in matrix notation. So then we are we are trying to remove this abstraction, right? I mean, we're trying to become like a bit more abstract, and then try to formalize things a bit. And so before we're doing like this, now everything can be done in terms of matrix. So what we have is like, you can represent this by this kind of matrix, and then you can also represent this by this matrix and this by this matrix. And then if you then you just do the matrix multiplication, then you will have some other matrix like this, and where phi is also phi 1 minus phi 0. And then each one you can write this U is a matrix. So then U0 0 you can write like this, and these are the components of the matrix. And so, and then the whole diagram, the entire diagram now turns into just one simple diagram. And then here you can see that if you start with a 0 the state, then the probability to go to 0 state is cos phi by 2, and the probability to go 1 it's minus I sine phi by 2 again. And then if you start with 1, then the probability to go to 0 is this part, right? So minus I sine phi by 2, and this amplitude, so you have to take the square. And then, I mean, what was it before? We got sine square pi by 2, right, before. So probability to reach 1 starting from 0. And then you can already see that because U0, so P10 is just U10 square, and then this is just this component, U10 is just this component. So minus I sine 5/2 square, and then just sine square 5/2. So it's the same answer. So that's the whole idea. So you have this complex interferometer, whatever you just convert it into the matrix form, and then all we will deal with from tomorrow onward is just matrix. So everything will be represented by matrix, and depending on and the idea is like if I have some matrix like this, and then if I go to the lab, and then if I talk to the experimentalist people, then they will tell me like how to implement this. And in this case, it was interferometer. Maybe like in superconductor, it might be different. In ion trap, it might be different. But it doesn't matter to us because it's just matrix. So that's the Dirac notation, what it does. Right? So you start with 0 and 1, and then yeah, everything is just a matrix from onward. So if you have questions here, then you can ask. Okay, so now like so this so you can also write the circuit diagram notation for that. So this part, this whole part, we can denote it by H, and then this part is just phase, and then this is H. So this is some kind of a circuit diagram notation for what we did before. So this part was, this H was creating superposition of 0 and 1, and this was creating this quantum interference, and this one was closing the interference. So this you will see this always in quantum algorithms and in quantum computing, because what it does is that this part, and we will call this Hadamard gate. So, and you always have to create a superposition at first, so that in all possible states, your what you want to compute will act, right? So because then you control this phase difference, because then what you want to do is like you don't want the wrong answer, so you want your probability amplitude to amplify in this so toward the correct answer. So then this interference term will do that job, and then to perform the measurement, like you cannot have like all possible superposition, so you need to close the interference also. I mean, you need to close the superposition. So this is what it does, everything over here. And then so this part is Hadamard gate, and this is phase gate, and this is Hadamard gate, and you start from something like that. And then these are qubits. So qubit is just a two possible quantum state, and this would also be in superposition. So here we have 0 and 1, and just like a bit, it can be in 0 and 1. I mean, qubit, it can be in 0 and 1 state also, but it's also possible to be in superposition. And how do you create superposition? By this kind of interferometer here, and we will call it a gate, Hadamard gate. Okay, so I think so now. Like I just have 15 minutes left, right? I mean, no. Okay. So if you have questions until now, like please feel free to ask. It's fine. So now, like I mean, I will finally talk about qubit. So what is qubit? So it's any two-level physical quantum system. So you have a 0 and 1. I mean, it's then it can be ground or excited state, or it can be, I mean, like I said many times, I mean, it can be spin up or down, doesn't matter. So it should be just like a genuine quantum system, and then what that means is that you should be able to create superposition. Right? So, for example, like what? Let's see, you start with a 0, and then so let's just say you start 0 now means a ground state, and then you send some light here, and then this electron, it will escape to this second state, excited state 1. So this is one possible way of doing quantum operation. So you applied some, and it just means that it's a NOT gate, right? So NOT gate means what? A 0 to 1, and also back. By sending light, you can also do that. But for example, like somehow, I mean, if pulses can take state, I mean, like if you don't, I mean, if if you don't send the total, I mean, if you just send the signal for half duration, like if you just send the light for half duration, then it's also possible that your electron, it can be in intermediate state, which is like a superposition of 0 and 1. So you don't know, I mean, you just send some light. I mean, if you send for total duration, then it will go from 0 to 1, which is just classical case, right? So it's a NOT gate. But if you apply this this pulses for only some time, then it's possible that it can be in superposition 0 and 1. Madam, it just means that you don't know where it is. So then we can write such a possible case like by alpha 0, 0 plus beta. Let's add alpha beta 1. And then so now, like if I, so for like this is a general case, and then if I send the signal for if I send the pulse light for some time, then I will get some kind of state like this. And then what this means is that if I perform the measurement many times, then the probability to get state 0 is alpha square, and the probability to get 1 is beta square. So that's the wave function. And so that's the most general qubit you can write, right? I mean, then it just means that you have 0 and 1. You can also have superposition, and you can convert superposition into probabilities by such. So here's what I'm. So you have alpha 0 plus some alpha 1, and then alpha 0 is the probability to be in state 0. Then alpha 1 is the probability to be in state 1, and then it has to sum up to 1 because all the probabilities, they have to sum up to 1. So it just means that if I look at the 0 and 1, I mean this electron will be somewhere, right? I mean, it can. So you won't lose the electron just by doing that. So that's what this means. So that's why, like your, I mean, like when you perform the measurement, then it will be either in 0 or 1. But you don't know already. I mean, you just know the probability of being in 0 or 1. And important is this alpha 0 and alpha 1, they can be complex number as well. Okay, so now like I said before, you can convert everything into this vector notation or matrix notation. Then everything simplifies a lot, and we don't have to deal with other stuffs. So we don't have to deal with the actual wave function of the electron, atoms, everything. So everything now from now onward will be just some pure matrix multiplication, right? So because so let's see. So you have 0, and then you can write in a vector like this, and 1. You can write like this. So this is okay. And then let's say you have some wave function alpha 0, 0 plus alpha 1, 1. Then it just means that alpha 0 plus 0, 1, and then it's just summing up, right? So alpha 0 and alpha 1. So that's the initial state. And then you need to evolve it. When you evolve, and then you get u of psi, and then you this u has to be 2 by 2 matrix. So then after that, what you get? So all you get is 0, 1 times alpha 1 times alpha 0. And this is the final state that you get. So you have initial vector, and then you multiply with some matrix, and then you will get some final vector. And in fact, like if you check here, I mean, you can also, I mean, okay, so I won't go, I won't say much. I mean, it's just, so what you can now do is like everything becomes very simple. I mean, everything just becomes matrix multiplication. So because you have some vector, and then you have some matrix, and this will represent the gate and evolution, and then this will represent the final wave function, and then this one will tell you the probability to be in 0, or this one will tell you the probability to be in 1. And then you can write like this, right? So this is the initial state, and then you evolve with some unitary, and then you get what? Psi 1. And the whole thing is just, so that's what it means. Or you could also have something else, like you start with psi, and then you have u, and then you again have some other evolution that's going on, and then you get psi bar. And then in this case, it's just you start with psi, and then you multiply with u, right? And then you multiply with b. So it's just matrix multiplication, basically. And okay, so let me see. So and then so these are just the quantum gates. So these are quantum state, and these are quantum gates, and you have like single qubit and single qubit gates. And tomorrow we will talk about what happens if you have like 2 qubit, and then your this matrix will not just be 2 by 2, but then it will be something else, right? So okay, so now like I just already said that these are gates. So now gates are just some quantum gates are just some matrices. And then, so for example, in classical case, what do you have? If you have not gate, then it will take 0 to 1, 1 to 0. In quantum, like we just not want, I mean, it's not enough to just send the 0 to 1 and 1 to 0, because you also have to take care of superposition. Then what it should actually do is, it should take 0 to 1, 1 to 0, and it should also do something like this. So alpha 0 plus beta 1, then it should also change 0 to 1 and 1 to 0. And that's what your quantum gate should do, and that's what like this unitary U should do. I mean, for quantum not gate, this is the example, right? So, and what are the properties of these matrices? First, they should be linear. I mean, they are already linear because they are matrices. So, and the second thing is they should be unitary. So this is very important property. So I mean, unitary just means that you have a matrix. If you conjugate and transpose it and then multiply, then you get identity. And then you can look at the literature, and then you can see that almost, I mean, every quantum gate, it has to be unitary. So these are the most important property of quantum gate. And then what is the one example? It's just this X gate, right? So this is the quantum NOT gate. And then let's see, like if you have X, then if you multiply with the 0, then it should give 1. If you multiply with 1, then it should give 0. And if it's multiplied with 0 plus 1, then it should give you. And let's see, like what was stated 0 before? 0 is 1, 0, right? So just multiply. I mean, it's just matrix multiplication now. Let's see. So then it's 1. So, and then if you do the same thing here, you will also get 0, 1, 1, 0. Then it's just 1, 0. And this will also be true. And then this is how like you can get a quantum NOT gate, and we call it X gate. So these are like single qubit gates. So are the unitary to preserve total probability to 1? I mean, yeah, it's true. Like this unitary, I mean, it's a very important property. So it will, and you always need it because it will help to conserve the probability. I mean, like otherwise you will lose some information, and then it will become all kind of messy stuff. So you don't want that. The other gate I want to talk about is Hadamard gate, and it's also just matrix. Right now it's just matrix, right? So it's just a matrix, and also very simple kind of matrices, because these are single qubit gate. I mean, it's just a 2 by 2 matrix. And we already talked about it. This Hadamard gate, it will create a superposition of 0 and 1. And if you multiply at Hadamard gate with 0, I mean, if you multiply this with state 1, 0, then you will get something like 1 over 1, 1, because you can try it. I mean, I will put the materials later on. Then if you expand it, then you will get this term, right? I mean 1 0 plus 0 1, and this is 0 plus 1. So if Hadamard gate it acts on state 0, then you will get the superposition of 0 and 1. And if you act on the state 1, then you will get the same thing, but with the minus sign here. So with a phase difference. So this is Hadamard gate. And the other gate we talked, it's a phase gate, which was like creating this phase difference. So what it does is, and it will, so if you act this gate on 0, then it doesn't change. But if you act on 1, then you get a phase term over here. I mean, then you can try it. Like you just multiply this with this vector, and then you will get this. It's not difficult. And when this phi is pi, then we call it z gate. Then because like if phi is pi, then this term is just -1, right? So what happens? Like if it will leave the 0 state, so it doesn't do anything to the 0, but it will leave 1 to -1. And when phi is pi by 4, it's called S gate. I mean, just terminology, but these are important gates. So Z gate is important, and Hadamard gate is important, and this NOT gate is important. So what do you have? Like, so if you have X gate, and then, I mean, for a more general quantum state, so what does it do? So you start with alpha 0 plus beta 1, and you act X gate, then this 0 will change, right? 0 goes to 1, 1 goes to 0. So, and if you act with Z gate, then check here, like what does it will not do? It will not do anything to 0 state, but it will change the phase of state 1. So 1 becomes -1. So alpha 0, it doesn't change, and this B becomes minus beta. Right? So you will get a phase term there. And then what happens if you act with Hadamard gate? Then we saw before this Hadamard gate, H gate will create a superposition of 0 and 1. So if you act on 0, then you will get superposition of 0 and 1. So H acting on 0 gives you 0 plus 1, and then on 1 it will give the same thing, but with a minus difference. So that's the Hadamard gate. So these are all the single qubit gates, and these are like a single. And then tomorrow we will talk about 2 qubit gates. And one very important property of 2 qubit gate is entanglement, because for entanglement you need 2 qubits. As you cannot talk about entanglement with just 1 qubit. So because they are like 2 things need to be entangled. Then once we do about 2 qubit, then we can already start talking about entanglement. Then we can already start talking about we can already start about 2 qubit gates. And also, I mean, you cannot do any computation just with single qubit, because you need interaction between 2 qubits at least, right? So then you just if you have this 2 qubit, then you will get like what is called universal set of gates. Then with that you can do like any kind of a quantum computation. I mean, in fact, like with quantum computers, you can also do classical computing. I mean, it's possible. I mean, so you can do both like classical and quantum computing. Okay, so I think that's it for today. Like if you have questions, then we can discuss. So I will provide these materials in Google Drive, and then maybe like organizer, they can send you.
Am I audible?
Yes. Yeah.
Okay, the course for today is now complete. I appreciate your helpful instructions, sir. We would be really grateful that attendees may ask their questions now. If you have any questions, please do ask.
Okay, so Hadamard gate. Okay, so let's see, like Hadamard gate, it's just Hadamard gate, it's 1 over square root of 2, 1, 1, minus 1. So this is the Hadamard gate. And right now, like we don't care about how to actually implement it in lab. I mean, it depends on the hardware, right? So we don't have to worry about that. So for us, it's just a matrix. And then as we discussed before, this one will, it's just a unitary operation, and then it will tell you the probability to go from one to other state. And then if this acts on Hadamard gate, if it acts on state 0, then it would create a superposition of 0 plus 1. Right, so let's see. So state 0 is just 1, 0. Then I mean just matrix multiplication. So 1, and then it's just 1. So then it's just 1 by square root of 2. State 0 plus 1. Right? And then this is just okay, so when the Hadamard gate acts on the state 0, then you will get superposition 0 and 1. And what it means is like, okay, so if I have some state like this, somebody gives me this quantum state, maybe 100 copies of this quantum state, and then if I perform the measurement, then the probability that I will get state at 0 is 1 over root 2 square, which is 1/2. And then the probability to get this state 1 is what? 1 over root 2 square, which is 1/2. So somebody, I mean, so I start with this state at 0, and then apply with Hadamard gate. And then if I have this state, and then I have like many copies of this state, then if I perform the measurement, then with 50% probability, I will get state 0, and with 50% probability, I will get state 1. And that's what the quantum superposition means. Okay. So hopefully it was, it helps. I mean, I understand that it's a lot of materials, right? I mean, it's quantum mechanics and everything, but so it also depends on your practice. And at the end, I think in 5th day, I will also show you some tools like these programming tools that you can use it, and you can even implement already in real quantum computer, in IBM quantum computer. So I will show you some tools later on.
Thank you, sir. A short notice, please. As mentioned already, your attendance will be checked thrice throughout the session. So please keep joining and stay throughout the session for your certificate. Once again, thank you everyone for joining. And I guess there might be one question again.
Yeah. So I think there are some questions. So Ritika, she's asking like why linearity is important. I mean, I didn't discuss much, but so this unitary gates, they have to be linear. I mean, so first thing you have to understand is that this unitary gate, it just means quantum evolution. You have some state and you evolve it, right? So linearity is like a really important property. Otherwise, I mean, I mean, there's a theorem called the no cloning theorem. So if I just give you some quantum state, then and then you don't know what it is, right? So I mean, you don't know like probability of 0 and 1. I mean, what is it? I don't know. And then it's not possible to have to design a machine which will clone the quantum state. And if you could clone, then you can even communicate faster than light. So this is a really important property to keep everything in balance. I mean, like if you combine, if you could clone any quantum state, and then if you use entanglement on top of that, then you can communicate faster than light, which is not allowed by relativity. So to keep everything in balance, like linearity is really fundamental. And not to mention like quantum mechanics, it's linear because I mean Schrodinger equation is already linear. So if you have one, I mean I want to put Schrodinger equation here, but let's just see like if you have some psi 1 is a solution of Schrodinger equation, then if psi 2 is also Schrodinger solution, then alpha psi 1 plus beta psi 2, it's also a solution of Schrodinger equation. So so quantum mechanics is already linear, but linearity is like very important. I mean, if quantum mechanics was not linear, then you could communicate faster than light. Yes, sir. Question, and the other question was like about Qiskit. Yeah, so I also it's called Qiskit, and I mean you can already go and check. All right, I mean you can already check. It's called Qiskit, and you can try playing with some of the tools there, and you can implement these gates that we talked about today. This X gate, Z gate, Haramet gate. But I will show you like how to do it at the end. Okay, so I mean if there are no more questions, then
If questions are done, I guess we may leave. Thank you everyone for your presence. Good night, everyone. See you soon tomorrow on same time. Thank you.
so thank you everyone for coming today. I mean maybe it was a lot of materials, but let's see how it goes. Yeah, so the notes. Okay, I will send the. I will put all the notes and some books that you can take. Then it will be available in Google Drive, and then then maybe the organizer. I will send this to organizer, and then they can send it by email. Maybe. Okay, then have a nice evening.
Thank you, sir. Good night.
Okay, good night.